and we're going to kind of transition now into chemical bonding. And we're still going to be really talking about the two similar types of compounds that we did with naming. So we're going to look at ionic bonding, and we'll also look at covalent bonding and talk about the differences. So let's take a looky here. So one of the ways that we represent sort of bonding, both ionic bonding and covalent bonding, is that we use Lewis dot symbols. Nowadays, people just use more of a generic, they call them sometimes electron dot symbols. It's all the same deal. And basically, a Lewis dot symbol or an electron dot symbol is basically the symbol and one dot for each valence electron that is present. So remember that when we look at valence electrons, they are the outermost electrons. They're the ones in the highest energy levels. They are furthest away from the nucleus, and they're not really held as tightly. And those are the electrons that are involved in bonding. Now, the other type of electrons, which are known as core electrons, those are closer to the nucleus. They are held a lot tighter, and they are not involved in bonding. So in bonding, we're not worried about the core electrons. It is only the valence electrons. And a reminder that when you go to the periodic table, as we talked about, you can very quickly determine the number of valence electrons as it equals the group number. So number of valence electrons equals the group number on the periodic table. So everybody in group 1 has 1, everybody in group 2 has 2, 3, 4, 5, 6, 7, and 8 at the end. A reminder that the one exception in group 8 is helium, because it only has 2 total electrons, so it can't have any more valence than it has total. So it has 2 valence electrons in there. Good news is, even though we talked about valence electrons in transition metal region, we never do anything with bonding in this class or in most classes with things in the transition metal region. So you don't really have to worry too much about any of those guys in terms of valence electrons, but they also equal the group number as we talked about. Remember though, that if you're going valence electrons for the guys in the middle, you got to kind of go the normal 1 through 18 numbering, right, to give you the proper number of valence electrons for those guys in the middle. So a Lewis dot symbol, again, is basically the symbol, one dot to represent each of the valence electrons. There really is kind of no major rule about how you should do that. Most people will usually kind of go around one at a time and then pair them up, but it doesn't really matter. The only main rule is you can't really go more than 2 per side. Yeah. So if you go 2 per side, there's 4 sides. That gives you a grand total of how many? 8 valence electrons. 8 is a magical number in bonding because who on the periodic table has 8 valence electrons? The noble gases. That is really the purpose of all bonding, both ionic bonding, covalent bonding, is for everybody to achieve the same electron configuration as the noble gases, which, as we just talked about, is pretty much 8 for everybody except helium is 2. And this is why it's really important, because when you look at the periodic table, hydrogen just needs to get to helium. So hydrogen, 2 valence electrons only. And I say that because people with hydrogen like to go crazy with it. They like to just like triple bond it up and, for good measure, pop some dots around it as well. Before you know it, hydrogen's got 400 electrons around it, and it should not have that. So if you don't want a big X, don't do that, yes? As I'll remind you as we go through this chapter again, that's pretty much what hydrogen should look like always, yes? No dots, don't pretty it up or anything like that. Leave it exactly like it looks like that. It should just look basically with one line, which represents 2 electrons, and hydrogen, again, if you're putting dots all around it, it's definitely going to be wrong, yeah. It is. We're gonna talk about, but in that particular case, that's usually where we'll see hydrogen in a lot of cases sharing electrons, because it is technically a non-metal. So as we talked about with naming, it will do actually covalent bonding and sharing of electrons. Yeah. So here's a bunch of Lewis dot symbols I made one time when I was bored. I should get a hobby. But you can see there, everybody in group 1 has 1, everybody in group 2 has 2. as we go across there, 3, 4, 5, 6, 7, and 8. Again, helium up there in the top right corner has only 2. Once again, you really don't have to worry about transition metals at all in terms of bonding, so don't even worry about it. So as we didn't talk about with naming, there's really 2 types of compounds. Again, ionic compound, and this again is how we want to recognize it. As soon as you see a metal and a nonmetal coming together, that is what should like scream in your head, an ionic bond. That is definitely all you need to know. All you need to identify is that's a metal and a nonmetal. That's an ionic bond for sure, which again means that there are no sharing of electrons here. We're going to get a complete transfer of electrons. When you have a covalent compound or covalent bonding, you see that when you see 2 nonmetals. Yeah. And as soon as you see 2 nonmetals together, what you should know is there's some aspect of sharing happening with electrons. So as we will talk about, we have sharing of electrons here and no sharing of electrons there. And again, much like what we talked about with naming, it is really important to take a look at what you're dealing with so you can understand what type of bonds happening and, are they sharing electrons? Are they going to transfer electrons? So it's always good to take that moment and try to identify what you're dealing with before you're just trying to jump in there and try to figure it out. A lot of this revolves around those periodic trends we talked about. Things with low ionization energy will tend to form cations. A reminder that ionization energy is the energy needed to remove an electron. So if it has a low ionization energy, you could just look at it and the electron's going to pop off. So it's not going to be very hard to do that. Things with high electron affinity. Electron affinity, again, a reminder, is the energy change that occurs when somebody gains electrons. So if you have high electron affinity, it means you're pretty darn good at gaining electrons. Yeah. So if you have a high electron affinity, that means that you're more likely to gain electrons, become negative, and you will be an anion. As we know from our periodic trend talk, that's our nonmetals that typically will do that, right? They typically will become negatively charged. And our metals over here to the left-hand side of the periodic table are the ones that typically will lose their electrons and become positively charged. So that's pretty much what I just said there. So metals basically going to lose electrons, non-metals going to sort of gain electrons. By the way, that's why with an ionic compound, when we have a metal and non-metal come together, we get that transfer of electrons because the metal's like, take my electrons. Non-metal says, I will because I want them. And we get the electron jump from one to the next. And that's how we get ions that are formed. And that's different, as we'll talk about with covalent bonding, where everybody's in the same location, basically in the periodic table, which means everybody there wants to hang on to their electrons. And they also want to gain electrons. So when 2 of those guys come together, neither one of them is going to give away their electrons, so they're just going to have to agree to share the electrons. So that's why we end up sharing electrons when we get 2 nonmetals together because of those periodic trends we talked about. That's why we get a transfer of electrons when we have a metal and a nonmetal get together on opposite sides, basically, of the periodic table. So let's take a look at an example like lithium fluoride. So lithium is group number 1, which means it has 1 valence electron. So if I draw the little dot symbol for that, and the electron configuration, a little 1s2, 2s1 action. And by the way, right there, that is the valence electron that we're looking at in the picture. So that is the valence electron. These 2 electrons here are the core electrons, not involved in bonding. And fluoride, which is fluorine, is group 7. So it's got 7 valence electrons. If we did a little electron configuration, 1s2, 2s2, 2p5, these are on the highest energy level. 2 and 5 is 7. Those are the valence electrons that we actually see in the picture here. By the way, when we see lithium, that is a metal, right? Fluorine is a non-metal. So right off the bat, I should know what type of bond I'm going to get here is going to be ionic, yeah? We're going to get a transfer of electrons in this case. And what's going to happen is that lithium is going to share its electron, not really share, but give away its electron, I guess is a way to look at it, over there to the fluorine. The result of that is at that point, lithium just lost an electron. It now has more protons than electrons, and that is where it becomes positively one charge, right? So it laid up as electron. On the other hand, our fluorine, who started with 7 electrons, just gained an electron. We'll make it red, why not? 1 electron there. Because it gained an electron, now it has more electrons than protons and becomes negatively 1 charged in that case. And now what we have are 2 ions, which is the basis of an ionic compound and an ionic bond. What holds this together is the attraction, which is sometimes referred to as the electrostatic attraction. That's a fancy way of saying positive and negative attracted to each other, opposites attract. That attraction between that, there is absolutely positively no sharing of electrons here. That is also why when we draw it for an ionic compound, there are charges on the right-hand side. Those charges indicate that the electrons are not being shared in this case. And a lot of times people will put a bracket around one like I did, and sometimes they'll put it around both just to indicate, again, that those electrons are not being shared in this particular case. So that is an ionic bond, transfer of electrons from the metal to the nonmetal. The metal then becomes positively charged in a cation. The nonmetal picks up the electron, becomes negatively charged and an anion, and now opposites are going to attract each other and they're going to stick together pretty strongly. That's a super strong attractive force, positive and negative attraction between them. First off, any question on that there? Why does this happen like it does? Well, let's see what happens actually with like the electron configuration. My lithium gave away that electron right there, right? And now ended up with 2 electrons, are an electron configuration of 1s2 when it has a positive charge. Who on the periodic table is number 2? That is helium. Helium is what type of element? Noble gas. That's pretty stable. That's looking good for lithium at this point, right? The fluorine had room right there in the p subshell because the p subshell can hold how many electrons? And it only has 5 at this point, right? So it's going to slap that extra electron right in there and have 1s2, 2s2, 2p6. If I count up the top numbers, that's 2, 2 is 4, and 6 is 10. Who on the periodic table is number 10? Neon. That is also what type of element? Noble gas, yeah? So this, again, is the purpose of all bonding, is for everybody to achieve the same electron configuration as a noble gas, because noble gases are extremely stable. Once again, does lithium become helium in this case? It does not, because protons did not change, right? The only way it could do that is to change protons. And fluorine does not become neon because it didn't change protons. But what it did is it ends up with the same electron configuration as the noble gases, and that creates a super stable bond. And that is really what happens in all ionic bonding, is typically speaking, the metals will lose electrons and back up on the periodic table to the noble gas that comes before it, right? So lithium's over there at 3 and helium's number 2. That is the noble gas that comes right before it. Nonmetals will accept those electrons and move forward on the periodic table to the noble gas that comes after it, creating a really stable sort of bond. Question on that there. By the way, things with the same electron configuration as we talked about are what are known as being isoelectronic with each other, right? Isoelectronic means that helium and lithium with a +1 charge have the same electron configuration, yeah? Question on that there. So again, like I said, absolutely no electrons being shared here. We have a complete transfer of electrons, which is what creates those ions, allowing each of those elements basically to end up in a noble gas configuration in terms of their electrons, creating basically a pretty stable bond. That again, as I mentioned, is the whole purpose of bonding, lower the overall energy of everybody to a really stable situation. Let's take a look at another example. Let's say we had calcium and oxide. As we know, calcium is a metal, oxide is a non-metal. So once again, what type of bond here? Ionic, yeah. And again, that is all you need to see to know it's ionic. Trust me when I tell you that. You will not get it wrong if you're asked what type of bond that is. If it's a metal and a non-metal, it's going to be ionic. So calcium is group number 2, which means it does have 2 valence electrons with an electron configuration. I'm just going to shorthand it a little. Argon 4s2. These are the valence electrons that we see in the picture, excuse me. And we have oxide, which is oxygen, as we know from naming. And oxygen is group number 6 on the periodic table. So it's got 6 valence electrons with an electron configuration of 1s2, 2s2, 2p4. Once again, based on those periodic trends, when these two guys get together, calcium's going to go ahead and take my electrons, and oxygen is going to go, cool, I'm going to do that. Thank you very much. Actual conversation that happens there. So this electron is going to come on over here because oxygen can handle it. By the way, if calcium just lays up 1 electron to oxygen, will it be happy? It will not. If you're not sure, you can look at the periodic table. If calcium loses just 1 electron, where's it back up to? Potassium. That's an alkali metal. Doesn't have the same ring as noble gas, right? So calcium here is going to want to get rid of both of those electrons. Good news is oxygen can handle both of those electrons. It's got space right about there because the P subshell could hold 6, and it has only 4 at this point. So we're going to get both of those electrons coming out from calcium. That's going to create calcium now with a +2 charge, becoming an ion. The oxygen there will pick up both of those electrons. And because it picked up 2 electrons, that means it's got 2 extra electrons and a -2 charge to come along with it. Yeah. Again, here, if we look at what happened with the electron configuration, the calcium got rid of its 2 valence electrons, which actually leaves it goes from 20 to 18. And again, that would be our 1s2, 2s2, 2p6, and 3s2, 3p6. Or as you can see there, that is argon's configuration, which is, again, a noble gas, group number 8 there. Also located 2 steps backwards from calcium, right? Moves you 2 electrons, 2 steps back, takes you back to argon. Once again, the oxygen will take both of those electrons right there, giving the oxide a 1s2, 2s2, 2p6, 2, 4, and 10 electrons, which again is neons. Once again here, by losing electrons and gaining electrons, both of these elements have now achieved the ultimate goal of bonding, noble gas configuration, to create this stable bond. Once again here, the attraction that holds this together is that +2 and -2 attractive force, no sharing of electrons here. Actually, that will be held together tighter than the first one. The strength of that charge increases with the size. So +2 and -2 will actually be held tighter than +1 and -1 as well. Question on that there. Yeah. 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 Are you asking what's he writing, like a +2 versus 2+? Is that right? It doesn't really matter. It's okay either way. I personally usually do number first and then the charge. But it's not technically wrong to do it the other way at all. So I think it's just a preference, probably what you just learned when you're younger going through it. But either way is fine. You do need that both combinations there, the charge and the number. So it's fine to do it like I did +2, or 2 plus. But if you wrote +2, it's perfectly fine as well. Yeah. But I would say most people will probably roll number first and then the charge, but it's really not wrong at all. Yeah. Other questions? Okay. So what happens though if we scribble all over that page? Let's try it here. What happens if we take our friend calcium that we just did and we put it together with fluorine from the first example? So calcium, again, having our argon 4s2 configuration, our fluorine having 1s2, 2s2, 2p5 in this case. So once again, that is still a metal and a non-metal, so we know it's going to be ionic. We know our calcium is going to give up its electron. So when it does so, it's going to send an electron over to fluorine. At this point, can that fluorine take any more electrons? It can only take one that it just took, right? At that point, it's full. Once again, will calcium be happy just getting rid of one electron? No, it needs to get rid of two. So in this case, it's not just one fluorine involved, but it is a second fluorine involved, which would be more than happy to take the other electron. The result of this is you will end up with a calcium that still has a +2 charge because it gave away one electron to each of the fluorines. You will have one fluorine that picked up just one electron. I'll just circle it. You don't need to circle it, but I will for this purpose. And becomes a -1 charge. Does not become a -2 charge because of -1 charge. The second fluorine, I'll draw it here, also picks up one more electron. Again, I'll circle it there to become a -1 charge as well. Now we have -1, -1, which is -2 and +2, right? The calcium has able to get rid of its 2 valence electrons, one to each, which means over here, our calcium ion becomes argon's configuration. Each of these fluorines will take one electron in that p subshell. And that means this guy up on top will have a 1s2, 2s2, 2p6, Ra neon configuration. This guy down here will have a 1s2, 2s2, 2p6, Ra neon configuration. Dare I say, all three of these guys now have achieved noble gas configuration. Yeah, they're all perfectly fine. Not a sharing of electrons happening here. Everybody is the charge, basically keeping those guys together. In reality, most people would probably draw it on that side because the minus charges wouldn't want to really be too close to each other, but it's okay. Why is this important? It's important for what we were talking about with naming and all that stuff. When I'm doing naming and writing formulas and I have a calcium with a +2 charge and a fluoride with a -1 charge, how many fluorides do I need to get me to that magical number of 0, right? When I add up the charge, the real reason you do that is this reason right here. It allows everybody to get to that noble gas configuration and actually create a stable bond. That is the reason why when we take ions, we want to put it together in the simplest way that will give the overall charge to 0, because in doing so, that will allow everybody involved to hit that noble gas configuration and be really, really stable. So that's really the reason why we say balance it out to 0. It's actually the bonding reason here is really why we do that. That again allows everybody to get 0. Because as we just saw, if you didn't balance it out to 0 and you just did something like this, you would have a +1 overall charge. And as we saw over here, he would not be happy, right? Because he only gave away one electron, right? So he's not going to be really stable. So again, that is the real reason why when we do ionic compounds, we want to make sure that those charges end up at 0 in the simplest way possible. It's really the bonding reason, getting everybody to that really stable configuration. question on ionic bonding. Yes, sir. Stability, they are in a sense, but not related to per se what we're talking about here. When we talk about stable and stability here, we're really talking about balancing everything, and that's going to allow really that bond to stay together. Yeah. Reactivity as well, it is related to that. So if you have something that's really unstable, it's going to be really reactive, right? And if you have something that's really stable, it could be less reactive, but it could still be pretty reactive if you put the right thing in front of it, basically, or with it. So um, again, what we're talking about here is there's energy involved in all bonding, right? And everybody has energy, right? Things are moving around. They have a lot of energy. So when we make bonds, the idea is to kind of get everybody together and lower the overall energy of everybody to a more stable situation. And by getting everybody into these really stable electron configurations, that it allows that to sort of happen. Yeah. Other questions? Yeah. Now that we talked about ionic bonding, let's talk about the other type of bonding that we've been talking about with naming. And clearly this one is not fixed. So yeah, those lines miss really badly. I'm just going to redraw those. All right, so covalent bonding is type 3 compounds, basically. That's our two nonmetals together. So again, recognizing what you're dealing with should help you understand the type of bonding that's happening. Should also help you understand what we're talking about with naming, what type of naming or how you should go about naming it. So again, I can't emphasize enough that one of the first things you should always do is try to identify what you're dealing with. Are they two nonmetals? Are they a metal and a nonmetal? So again, it should point you in the right direction. Covalent bonding is sharing of electrons because, again, as I mentioned earlier, this is between two nonmetals, which basically they both want to hang on to their electrons and they both want to take somebody else's electrons. So, like I said earlier, the best that they could kind of agree upon is, hey, let's just share them maybe and try to get everybody happy in that situation. So there is going to be sharing of electrons here. And as we will talk about that, sharing of electrons may be equal sharing or unequal sharing. But there is some aspect of sharing of electrons here, and that is very different than ionic bonding where there is no sharing of electrons. We're just going to see those electrons transfer from one side to the next. So Gilbert Lewis suggested the role of covalent bonding, and hence why we call it Lewis structures, Lewis dot symbols after this guy. So I'm just going to redraw this because I'm not sure what happened to all the dots and stuff. So we had two hydrogens. Obviously, in this case, they are both hydrogen. They're both nonmetals. They're both the identical element, which means they have the exact same periodic trends, which means neither one of them is going to want to give away their electrons. So what they're going to agree upon is let's just share those two guys in this case. And what will happen is they will actually share the electrons between them. So the two electrons between them will count for the hydrogen on the left, and the two electrons there will count for the hydrogen on the right as well. That will ultimately give each hydrogen two electrons. Is that good or bad for hydrogen based on its location on the periodic table? It is good because it's going to move hydrogen now forward to helium, right? And that is a noble gas. So boom, we have just hit some stability there. You can represent this with dots like I showed there, without the circles usually. You can also represent this type of bonding, which is a covalent bond, with a line. And a line would indicate electrons are being shared in a bond. Each line represents two electrons or a pair of electrons. So this is a single bond, which is basically the sharing of two electrons or one pair of electrons. You could have, as we'll see a little bit later, two lines, which is the sharing of four total electrons or two pairs of electrons, and that is a double bond. Or you could have the three pack of lines there, which is a triple bond, the sharing of six electrons or three pairs for a triple bond. And again, most of the time I would say people will show bonding by using the line, but it is absolutely not incorrect to use dots. So if you want to use dots, you could use dots to represent it. It's not incorrect or anything like that. What holds those together, which is a covalent bond here, is the attraction of those negatively charged electrons to like the nucleus, which is positively charged on each of these, right? So there's a positive charge on each of these guys. Those negative charged electrons between them are attracted to like the hydrogen on the left, but also attracted to the hydrogen on the right, and it kind of locks them in place between the two atoms. And that's what creates the sharing of electrons in this particular case. Any questions on that? And again, in this case, we definitely have sharing electrons. And like I said, that sort of mutual attraction to each nucleus will basically lock everybody into place. Now, if we take something like fluorine, for example, and fluorine again is group 7 on the periodic table, and it will have 7 valence electrons, and we put it together with another fluorine, which also would have 7 valence electrons. Once again, these two guys for sure are going to decide to share those electrons because, again, it is 2 nonmetals together. So once we see 2 fluorines, which are 2 nonmetals, I know I got sharing of electrons happening here. Again, like I know when I have a metal and a nonmetal, I have transfer of electrons. So in this case, we could draw this. A little bit of action there and a little bit over here. And when we share those electrons in the middle, the fluorine on the left will now gain 8 electrons. And sharing those electrons in the middle with the fluorine on the right will also give that fluorine 8 electrons. Once again, on the periodic table, 8 electrons is noble gas, yeah? So noble 8 valence electrons is the noble gas configuration. Again, here by sharing those electrons, they're able to achieve noble gas configuration. Again, we could also represent this with a line to show the bond, which is probably most common the way people would draw it. And again, that line in the middle would represent 2 electrons that are being shared in this case. Question on that there. So when we look at something like this in a Lewis structure and we see the dots and we see the lines, they do represent different types of electrons that are there in this sort of structure. And let's talk about what each of those sort of things represent. And they represent, for example, all those dots which are not involved in bonding. And I know they're not involved in bonding because there is no element on the other side of it. They are what are referred to mostly nowadays as non-bonding electrons, but if you're old like me, lone pairs is what most people call it sometimes. So if you hear somebody say lone pairs or you hear somebody say non-bonding electrons, it's the same thing. They're the electrons that are represented by dots in the Lewis structures. They're not involved in any type of bonding happening. And again, I would say books nowadays kind of use more non-bonding electrons than lone pairs, but sometimes lone pairs pops in there. It probably will pop in from my mouth, to be honest with you. So again, if I say lone pairs, non-bonding electrons, same deal. Now, the electrons there that are involved in a bond has a special name as well, and it's very creative. They are known as bonding electrons, which kind of makes sense. So the actual electrons are involved in a bond formation are known as bonding electrons. The ones that are not involved in any type of bonding, represented as dots on the Lewis structure there, are non-bonding electrons, are lone pairs. Any questions on that there? When you draw these things, you should always show all those electrons. So you should always show all the non-bonding electrons. You should also always show all the bonding electrons as well. So a Lewis structure, again, is a representation of covalent bonding where we show those electrons being shared through a line or dots. It is important to remember that although we only show the valence electrons in these structures, they obviously have more electrons. They're just not involved in bonding. So, when we show something like, say, lithium or fluorine. Fluorine has the 7 valence electrons, but it still has those lower energy electrons as well. They're just not involved in bonding as well. Now, if we take a look at another example of this, water. And water here, by sharing electrons, as you can see in that picture there, I'll draw it up a little bit higher, with the actual 2 hydrogens, will allow the hydrogen here to end up with 2 valence electrons. This hydrogen, on the left will also end up with 2 valence electrons as it shares with the oxygen. And the oxygen, by actually sharing with both of those hydrogens, will hit that magic number there of 8. And again, through all this sharing of electrons, everybody again is able to hit that noble gas configuration, which, as I mentioned a number of times by now, is really the whole purpose of all bonding, basically, is for everybody to end up basically right over there in group number 8 in terms of their electron configuration and be really, really stable. So that brings us to what we've kind of been going around. The official name, obviously, for 8 in bonding is what is known as the octet rule. And the octet rule means 8, basically. It means that everybody will continue to make bonds until they have 8 valence electrons around them. So they'll just keep on going until they get 8. Except for who that should never have 8? Not helium, but the one before it? Hydrogen, yeah. So again, hydrogen never have 8, should only have 2. And that is sometimes what is referred to as the duet rule. And like I said before, never hurts to say it because I've seen a lot of weird looking hydrogens come through pages. It should pretty much always look like this. It also means that when you are drawing pictures, you should keep in mind that hydrogen should never be in the middle of the picture, because if it's in the middle of the picture, it most likely will have way more than 2 electrons. So hydrogen should always be on the outside, just hanging on by 2 there, and never in the middle, because it will also have way too many electrons. Okay. So multiple bonds, as we kind of talked about on the previous slide, there are single bonds. Now, the idea here is this: sometimes to get people to the octet rule, all you simply need are single bonds. Single bonds are perfectly good to do that. Gets everybody to the octet rule. Once again, the single bond, as I said earlier, a single line to represent it that represents 2 electrons or a pair of electrons. A double bond is actually sometimes needed to get people to the octet rule. So sometimes single bonds are not enough to get everybody to that stable configuration. You need a couple extra bonds there, and you're going to need to make some double bonds. CO2 is an example of that. So again, CO2 actually will make a double bond on both sides, and that is actually necessary for everybody to get to 8. So how does everybody get to 8 in this case? Well, if we just kind of highlight things, this oxygen has 2, 4, 6, and 8 through the double bond there. This oxygen on the right, 2, 4, 6, and 8 electrons. The carbon in the middle will also have 8. I'll use a different color maybe. 2, 4, 6, and 8 electrons. So in this case, in order for carbon to actually be happy and get itself to 8 electrons, it actually needs to lay up a couple double bonds. And that's sometimes the case. Sometimes it may just need 1 double bond will be sufficient, but sometimes you may need 2 to get yourself there to that. Again, a double bond is 2 lines representing 4 total electrons, are 2 pairs of electrons. And sometimes double bonds is not enough to get everybody back over to the noble gas configuration. So sometimes you do need triple bonds to do that. And a triple bond is, as we can see here in nitrogen, nitrogen actually needs to make a triple bond with itself to be happy. This guy we'll see in organic chemistry. Those carbons there actually needs to make a triple bond as well with itself to be able to do so. That's going to give hydrogen 2. This carbon here 8. This carbon here, 8. And that hydrogen there, 2. So that's going to give everybody the stability that they need. 1, 2, 3 for a triple bond. 6 pairs of electrons. Oh, not the pairs. 6 total electrons. 3 pairs of electrons. Side note on this, when we talk about drawing these things, sometimes people get carried away with it and they just want to like double bond out of the box, triple bond out of the box because that looks more chemistry like, right? So I'll just tell you this now and I'll tell you it again. You shouldn't do that. Yeah. So you should really start with single bonds. And if that doesn't work, you should then go to double bonds. And if that doesn't work, you should go to triple bonds. In most cases, double bonding or triple bonding right out of the box, not going to get you the right picture. Yeah. So you kind of want to go in that progression, single bond. If that doesn't get everybody there, double bond. If that doesn't get it, triple bond. That should get it, or you did something wrong at that point. In most cases, you probably won't go more than that. So let's talk about this sort of sharing of electron and how we know how the sharing is going to happen. So we're talking about covalent bonding and we're talking about sharing of electrons. And as I mentioned before, that sharing can be equal or it may be unequal sharing of those electrons. And it is that electronegativity, which is really the big factor to determine how electrons are going to be shared. You could also use electronegativity to help you determine if you have an ionic bond, but the truthful answer is you don't need it because I know I have an ionic bond when what two things come together? Yeah, so as soon as you see metal, non-metal, that's all you need. You don't need anything other than that. But for covalent bonding, when we do have sharing of electrons, electronegativity can be very helpful for you. Again, a reminder is, I think we talked about it when we did some periodic trends. Electronegativity is the ability of an atom to bring electrons towards itself. And on the periodic table, also known as a square, it increases as you go up to the right and it decreases as you go down to the left. Fluorine is the most electronegative element you could have. And that is because if you look at the periodic table, fluorine is as far up and to the right as you could go. Everybody to the right of fluorine is a noble gas, which means they're perfectly fine by themselves. They're not looking to do anything and they're not looking to react because they're already stable and stuff like that. So how can we use electronegativity and what helps us decide, how electrons are shared? If we take an example like H2, obviously in this case, they're going to be sharing those electrons. And in the case of hydrogen on the left and the hydrogen on the right, they are the same hydrogen basically, right? They have the exact same electronegativity, which means when these electrons in this case are shared, they are actually going to be shared equally because they're both going to pull those electrons exactly the same. Kind of like tug of war, right? If somebody pulls the rope on each end equally, the little flag in the middle is not going to go anywhere, right? It's just going to be stuck there. So if you take a look at this and this kind of red smear or whatever I'm drawing up here is the electron density, we're going to have kind of equal sharing of electrons. And when we have equal sharing of electrons, that is what is known as a nonpolar covalent bond. I would say most people leave the covalent out of it and just call it a nonpolar bond. So they are the same, basically. It is usually implied that if it's a nonpolar bond, it's covalent, there's sharing of electrons, and they're equal. Because these electrons are going to be shared equally, this is essentially a neutral bond. There is no like positive side, there is no negative side. All the electron negative stuff is all spread out nice and equally. Everything's sort of balanced. So this is kind of like a neutral or no charge situation happening in this bond. Again, there is no positive side or negative side. And that is a nonpolar covalent bond, equal sharing of electrons. Now, what would happen if I swap out the hydrogen or one of them for fluorine, for example? Now, in this particular case, based on electronegativity values, which one is more electronegative? Is the fluorine, is the most electronegative. So what's going to happen in this case is the electrons are going to be more attracted to the fluorine side than the hydrogen side. So what's going to happen is, if I kind of do my little bad scribble here, if this is like electrons, most of them are going to hang out over there on the fluorine side rather than the hydrogen side. What that does is it makes the fluorine side, if you had to guess, more positive or more negative. If all the electrons are hanging out on fluorine, it should be more negative, right? Electrons are negative. So it creates a partially negative charge on the fluorine. That's a delta symbol. It means partial negative. It also creates a partially positive charge on the hydrogen because the electrons are moving away from the hydrogen. It's becoming what is referred to as being electron deficient, right? It's losing like those hydrogens. You can represent this as well with an arrow. And this arrow is what is referred to as a dipole arrow, where it always points to the more negative side of the bond. And the back part that kind of makes like a plus sign is the more positive side of the bond. And this is what is sometimes referred to as a dipole arrow. These electrons are now not being shared equally. So no equal sharing, right? Or unequal sharing, I guess, is another way to write that. This is what is known as a polar covalent bond, or just a polar bond. Final question of the evening. Why are these partially negative charges and partially positive charges? And why are they not full positive charges and full negative charges? Yeah, so it has to do with, when we're talking about covalent bonding, what is happening with those electrons? Are they being transferred or shared? Being shared, yeah. So even though they're not being shared equally, there is still some aspect of sharing. If you want to go back to the tug of war example, the hydrogen is just barely hanging on to that rope. The fluorine is dragging it across the grass, right? But he's still hanging on. So because there's still some aspect of sharing here, we get actually partially positive charge and partially negative charge. In an ionic bond where there is no sharing of electrons, we get a full transfer of exactly zero. They will sometimes classify that as a pure covalent bond. And a pure covalent bond is still a nonpolar bond, but it is like as perfect equal sharing as you could get, basically. So it's like a perfect equal sharing situation. It's still considered a nonpolar bond. A reminder that when we have a nonpolar bond, it is essentially a neutral bond, right? Because we've got equal sharing of electrons. So if we have a nonpolar bond between these two guys, that bond right there is essentially going to be neutral. There's no like positive side or negative side, because overall the electrons are being shared equally. When we have a polar bond, a reminder that we do get that unequal sharing of electrons, which does create a bond that is sort of charged. One side is, for example, partially negative, one side is partially positive, and the side that's partially negative would be the side that is more electronegative, right? It will be where those electrons are hanging out basically more than the other side. As we, I think, talked about as well last time, they are partial positive charges and partial negative charges because there is still some aspect of sharing happening there. So the electrons haven't fully jumped from one side to the next. They're still hanging on, but they're not hanging on equally between the two. And again, that's what creates these sort of partially charged parts to this bond. And that's really important for later on in some chapters. of how, for example, molecules interact with each other, if they have that sort of charge or not charge, and that will allow them to sort of interact. Any questions on that there? So let's take a look at this table here, or a table like that. Actually, we'll go with the bigger one. It's got all the numbers on it. Why not? Obviously, these numbers would be provided for you if you needed them. But actually, we'll back up to this one. We could probably borrow this one for this. Will work for what we have. Yeah. So let's take a look at the three sort of examples of bonds that we talked about. We had our sodium chloride again that we looked at. We had our HF, and we have like our F2. And again, when we look at these guys here, we can use the difference in electronegativity values to help us decide what type of bond is going on. Once again, if I go to the table, I can see fluorine is 4 for its value, and this guy is 4 as well. So to calculate the difference in electronegativity, we're just going to simply take 4 minus 4, and that's going to give us 0. And that 0 obviously falls between 0 and 0.4 on that little scale that we just talked about, and that's going to make us a nonpolar bond. It really is a pure covalent bond that's going to be like perfect equal sharing of electrons between those two, because really they're the same element. If we come over to our hydrogen here, hydrogen onto there is 2.1, fluorine is 4. By the way, when you do this sort of subtraction, you just take the larger number minus the smaller, so you always get a positive number. It's really the difference, so you could do it either way, but just do it so you get a positive number. So we'll take our change in electronegativity, 4 minus 2.1. I'll go with 1.9 in that particular case. 1.9 puts us between 0.5 and less than 2, and that would tell us that that is a polar bond. Remember, we could draw those bond dipole arrows that will actually point towards the more electronegative guy, and in this case, it would point towards the fluorine, which is more electronegative. And again, the back part of that arrow that makes kind of like a plus sign will be to the sign that's more positive. So the fluorine here in this bond would be more negative, and this guy would be more positive. Once again, that arrow is what is sometimes referred to as a bond dipole arrow. And again, it always points to the more negative side, and the other guy is where the positive side is there in that particular case. Now, lastly, here we have sodium, which is 0.9 on the electronegativity scale, and chlorine, which is 3. So once again, just taking the larger number minus the smaller number, 3 minus 0.9, that's going to give us a 2.1. That 2.1 is above 2 technically, and that would tell you that it's going to be an ionic bond. But as you could maybe see, if you just kind of look at some combinations here, it is definitely possible, you know, that you could get less than 2. For example, if you maybe pop those two guys together and subtracted them, you get less than 2, but it's still an ionic bond. So again, I wouldn't even worry about electronegativity for ionic, but you definitely could help you for polar or nonpolar. Question on how to do that there. All right, so let's just try some here. Are the following bonds ionic? Is it polar or nonpolar bonds? And it's the bond between, say, carbon and oxygen, the bond between sulfur and oxygen. Let's do carbon and sulfur. Let's also do carbon and hydrogen. Let's do a little lithium and chlorine. All right, so take a moment to calculate the difference in electronegativity and determine, is it ionic, polar, or nonpolar, each of those bonds. If it is a polar bond, draw the arrow pointing in the right direction. Yeah, the dipole arrow. Okay, so let's take a look. So once again, these values would be provided for you. You just want to kind of find the two ones that are within the bond. So we'll start with the carbon and oxygen. So from the table there, we can see it's 2.5 for the carbon and 3.5 there for the oxygen. Once again, we're just going to take the larger number minus the smaller. So that would give us a difference in electronegativity of 3.5 minus 2.5. That will give us a 1 as our difference. That is going to put us here between those numbers, the 0.5 and below 2, and that would tell us that this bond here would be a polar bond. Now, because it's polar, I could draw that dipole arrow. It should point towards which element? Should point towards the more electronegative, which in this case would be the oxygen, right? So it should actually point in that direction. The oxygen would be more negative than the carbon, as more electrons are kind of hanging out on that side of the bond. Question on that one there. Between sulfur and oxygen, sulfur 2.5, oxygen still 3.5. That is, believe it or not, can give me the same difference there. Difference in electronegativity, 3.5 minus 2.5. That's going to be not 0. That's going to be 1. And the difference there again will put us back into there. And this would also be a polar bond because of the difference in electronegativity. Again, in this case, we would also draw the arrow pointing towards the oxygen, as it is more negative in this bond. When we look at carbon and hydrogen, carbon is 2.5, hydrogen is 2.1. Difference in electronegativity, 2.5 minus 2.1. That is 0.4 difference. 0.4 difference actually puts us right here. And that's really the reason for the 0.4 cutoff, because that's an organic type of bond, and our organic molecules are nonpolar. And it would actually be a nonpolar bond in this case. Because it's a nonpolar bond, we do not draw the arrow. The arrow, again, is only for polar bonds, because in a nonpolar bond, they're going to be sharing those electrons equally. Again, you can think of it like a neutral bond. There is no negative side or positive side in that situation. Question on that one. All right, let's go carbon sulfur here. So carbon 2.5, sulfur 2.5. That is going to give us a difference in electronegativity of 2.5 minus 2.5. That is a 0. And that would then obviously put us in a nonpolar bond. This also would be considered a pure covalent bond, as it's like perfect equal sharing of electrons in that case. And again, we would not draw a molecule, I'm sorry, an arrow here, as it is a neutral bond. Now, that brings up a good point, that is basically two different elements that actually share the same electronegativity, and that can happen. So if you have two elements that are the same, obviously within a bond, they're going to have the same electronegativity, but you could also have two elements that share the same electronegativity that are different. The relationship that comes from is what is sometimes referred to as the diagonal relationship of on the periodic table. Carbon is here, sulfur is there. They're like diagonal of each other, not directly below, but kind of one over. Same thing over there with nitrogen and chlorine. You'll kind of see that happen as well. One is further up, but one's further to the right. So they kind of cancel out their differences in terms of electronegativity, and they actually end up with kind of the same value. So diagonal relationship sometimes occurs, and you can get two elements that are different elements, but actually do share the same electronegativity values. We look at lithium here, which is 1. Chlorine, which I wrote all over, is 3 in this case. So difference in electronegativity going to be 3 minus 1, which is 2. And that is going to be an ionic bond. But as I mentioned before, don't even really need that. That's a metal. That's a non-metal. That's all you need to know for those two to be able to really know that it's ionic. And that's how I would go with it for those two. Question on how to use electronegativity values there. Now, do you always need the actual values? The answer is no, you really don't. You can pretty much make a pretty good estimate just using the general trend in electronegativity, especially, for example, if you're looking at something that's either in the same group on the periodic table or the same period on the periodic table. We look at our carbon-oxygen bond from earlier. They are in the same group on the periodic table, and oxygen is actually further to the right, and I'm sorry, they're in the same period on the periodic table, and oxygen is further to the right, and that would make it actually more electronegative and will yield you a polar bond. You don't even really need the numbers. We could also look at our sulfur and oxygen sort of combination. That guys are in the same group, and oxygen is further up in the group than sulfur. And that also will get you a polar bond and a difference in electronegativity. So if you're comparing two elements that are in the same period on the periodic table, are the same group, and they're away from each other, which they most likely would be, it probably will be enough to give you a polar bond in that case, and you can pretty much make a pretty good estimate as to that. Any questions on, again, using that there? Okay. So as I mentioned, atoms with really widely different electronegativities will tend to make ionic bonds. And again, that's really because as you get somebody on the left-hand side of the periodic table with somebody on the upper right of the periodic table, there's going to be a pretty big difference in that electronegativity values. And that's going to make, for a lot of reasons, the electrons jump from one to the next, from the metal to the non-metal. But when you crowd everybody here in the non-metal region, like we have with covalent bonding, everybody has similar electronegativity values, not enough to cause the electrons to jump from one place to the next. They're just going to actually share electrons in that particular case. And there's from your book there, are similar in your book there, the cutoffs that we talked about there. Basically 0 to 0.4 nonpolar, equal sharing of electrons, 0.5 and above to below 2 polar, more than 2 usually going to be ionic. Now, when we have some sharing that is like 0.4, is it like perfect equal sharing? It's not. There is some unequal sharing happening, but it's not enough to be considered totally unequal sharing. So there's sort of a limit there. Any questions on that there? All right. So now what we're going to talk about is drawing Lewis structures for covalent bonds and covalent molecules. And by the way, what we just talked about there with the electronegativity difference, it was sometimes referred to as bond polarity. So difference in electronegativity basically tells you, in most cases, just between these two atoms, how the electrons are going to be shared equally or unequally. It does not always tell you in the entire molecule how everybody's going to share the electrons, but it tells you how just between those two things, which is why I sometimes refer to as bond polarity, how those two guys are going to share the electrons. We will talk about it a little bit later, but in some cases it actually will tell you the whole story, but in other cases it will not. So it kind of depends on the situation. If that's your question, we'll get to it. Yeah. Yeah. It does affect the polarity doesn't necessarily affect the shape of it, but it does affect you know, how many types of electrons you have around the central atom, stuff like that. That affects the molecular polarity of it, as we'll talk about. But also the types of electrons that are around it, the central atom, as we'll talk about, affects the actual shape of it. Yeah. All right, so I would recommend that you perhaps follow these instructions on how to draw these Lewis structures because they will get you to a pretty good picture when it's all said and done. If you try to do it like a lot of people do, and I call it kind of like do it by piecework, like, you just kind of take all the individual elements and Lewis dot symbols and try to figure out how all the electrons kind of come together. Usually you're going to end up with a picture that's probably got not the right number of bonds, too many electrons, not enough electrons. So what we want to think about as we're doing this is we just want to kind of distribute the electrons as sort of equally to everybody as possible. And that usually will end up with, a pretty good structure. So one of the first things that you want to figure out is, if you're not sure, how everybody is sort of hooked up together, how everybody is sort of bonded together. And that's sometimes referred to as the skeletal structure. So to help you make that decision, there are a couple of rules that you want to follow. One rule is usually the least electronegative atom is the one that's in the center. So we usually want to put the least electronegative atom in the center. I would say probably for you guys in this class and in a lot of cases, there usually will just be one guy in the center and like everybody else is sort of attached to it. That's not always the case. It is possible to have multiple center atoms and multiple things attached, but probably most of the things that you'll probably come across until we get to maybe some organic things, but it will be like there's one guy in the middle and then like everything else is sort of attached to it. That means that hydrogen and fluorine should never be in the center. That's because fluorine, as we just saw, is the most electronegative element, so it should not be there because it's not the least. And the reason we shouldn't put hydrogen in the middle is what's going to happen if we do. Like if I laid up hydrogen in the middle and then put some other things around it, what happens to my friend hydrogen? It's got like way too many electrons. Yeah, so never ever again should we put hydrogen in the middle. Hydrogen again should simply be on the outside, kind of looking like that, pretty much one line or one bond to it. And again, never should be in the middle, otherwise it's going to end up with too many electrons. Probably the most important thing that you need to do is really number 2, and that is to count up the total number of valence electrons in the entire molecule or ion. And again, we could get the valence electrons from the periodic table and the group number. Now, if you come across something that has a charge, like a polyatomic ion that we talked about, you do have to take the charge into account when you're adding up everything. So if we have somebody that has a negative charge, we need to add to our total. So if you have a negative overall charge, we need to add those electrons to our total. And if we have something with a positive charge, we need to, it's actually positive there. We need to subtract that positive charge from the total. So you do have to adjust it. Again, if you don't do that, you will be off. You'll have not enough electrons or too many electrons, so you do need to adjust it. If it's obviously neutral, you don't have to worry about that. You just have to get all of the valence electrons. Once you have sort of the logical arrangement of how everything should be put together, and once you figure out how many electrons you need in your picture, and that number is really important because when you're done with your picture, you got to hit that number on the nose. You can't have any more or any less electrons. It has to hit that exact number with your picture. What you want to do, which is again a very common mistake that people make, is they want to double bond and triple bond right out of the box because again, it looks more chemistry like, and that usually leads you to a pretty bad structure and stuff like that. So you do not want to double bond or triple bond out of the box. You want to take whoever's in the middle and you simply just want to make one single bond to everybody. Remember that one line represents 2 electrons, right? So that represents 2 electrons in this case. You want to count up how many electrons you just used. So each of these lines, 2, 4, 6 electrons. I basically just used in my made up picture. All the remaining electrons go on the outside atoms first in pairs of electrons. So these are dots on the outside atoms, and then you work your way in. So always on this deal at this point, we want to work outside in to do so. So we would go around until everybody obviously has 8 valence electrons around them. We would put them on as dots of electrons. And if you filled up all the outside atoms with pairs of electrons and you still have electrons to go, then you go to the center atom. So again, working outside in, and that's where you lay up a couple of dots perhaps, also comes on as pairs of electrons. At this point, once you get to the center atom, you should be out of electrons, or something's not so right in this class for sure. You definitely should be out of electrons at that point once you put them onto the center. Once you've done that, what you want to do is you want to go around everybody and you want to make sure that everybody has met that octet rule, that everybody has 8 electrons around it, except for obviously hydrogen that should only have 1 or 2 electrons around it. It is at that point that if somebody has not met the octet rule, that's when you should try a double bond to fix it. So you want to kind of think of a double bond or even a triple bond as an effort to fix somebody that has not met the octet rule. So you would make perhaps 1 double bond and hopefully that works. If not, then if you have an option for a second double bond, you would want to make a second double bond at that point. If by some chance all your double bonds doesn't work, then you should move to your triple bond. So that's sort of the order that you want to do. You want to start with single bonds. And then at the end there, if somebody doesn't have 8, you want to try to fix it with a double bond. And if you cannot fix it with a double bond, then you want to go to a triple bond. So again, that's sort of the order at which you want to draw these things. Any questions on that there? All right, so let's do one here together to see these steps in action. So we have NF3. So the first thing I'm going to do is actually just calculate the valence electrons. So we got 5 for nitrogen, right? Because it is group number 5 on the periodic table. I have 3 fluorines. Each is group 7 on the periodic table. It's a lot of math for late at night. It's 21 and 5 is 26 valence electrons there. So again, that number is really important because I have to hit exactly that number when I'm all said and done. So the next thing I want to think about is, what is the logical arrangement? Well, I have 1 nitrogen and 3 fluorines. I would say in most cases, if you have 1 element and 3 of something else or 4 of something else, probably the 1 guy goes in the middle. Yeah. I know he also should go in the middle because between nitrogen and fluorine is more electronegative, right? So we just talked about fluorine cannot go in the center. So it has to be nitrogen, which is the least electronegative in the center. So I'm going to do a nitrogen in the center. I'm going to put some fluorines around it. And to answer maybe the question you might have, yes, it doesn't matter. You could throw the fluorine up on top if you like. It don't really matter if you want top or bottom there with that fluorine. I'm going to do 1 single bond. And I'm going to show that with lines to represent those bonding electrons. I did 3 lines in this case. Each one represents 2 electrons. That is a total of 6 electrons I basically just put on my picture. I now have about 20 electrons still to go. At this point, again, we're going to work outside in. So pairs of electrons, so pairs of dots. So 2, 4, 6. That guy is full. 8, 10, 12. That one is full. 14, 16, 18. At this particular point, I just put another 18 electrons up there. I still have 2 electrons to go. Everybody on the outside is filled. So now we go to the center and we put them on as pairs of electrons. At this point, I have now put on my picture the 26 electrons that I need. Last thing I want to always check is to make sure everybody is happy in terms of the octet rule as well. So if we look at this fluorine on the right, 2, 4, 6, and 8. So he's good to go. This one's identical, 2, 4, 6, and 8. This one's also identical, 2, 4, 6, and 8. And when we look at the nitrogen, 2, 4, 6, and 8. Everybody has 8 valence electrons. And everybody will be happy with a little highlighting going on there. Yeah. Any questions on that there? Okay. So again, you want to kind of follow these steps. You want to think of, you really want to think of the electrons as not necessarily belonging to anybody, but again, we kind of want to distribute it as equally as possible. And again, that usually will get you to a pretty good structure when it's all said and done. Any questions? So why don't you try this one? Why don't you try NO3 minus? So that's nitrate. And see what you come up. Okay, so let's take a look, see how you're doing on this one. Again, we're going to kind of follow the same procedure here. I'm going to get the valence electrons, which is really an important number. So once again, nitrogen is group number 5 on the periodic table right there. That means it does have 5 valence electrons for our nitrogen. We have 3 oxygens, which are each group 6 on the periodic table right next door. And once again here, I do have a negative charge, which means what do I need to do with that? So when we have a negative charge, did we lose or gain electrons? Gain, right? So I do need to actually add that to my total. Otherwise, I'm going to be short in this case. So because of the -1, I do need to add 1 more in there. Again, otherwise you will be a little bit short there. That's 18, 19, 24 valence electrons. Again, if you had a positive charge, you would need to subtract 1 because it lost electrons. So again, that's really important to sort of adjust the total in that case? Well, when we look at nitrogen and oxygen on the periodic table, they are right next to each other in the same period, which means if we go this way, oxygen is actually more electronegative. So clearly here, nitrogen should be in the middle. By the way, once again, just logically thinking about it, you got one nitrogen, three oxygens. Probably again, that one guy is going to be in the middle in most cases, not always, but in a lot of cases it will be. So we're going to rearrange this here. Just going to kind of put my oxygens around it. And just like in the first one, it doesn't matter if you put the oxygen on top or bottom there in the middle. We're going to do our single bond to everybody. So a bond there, a bond there, a bond there. That again is 2, 4, 6 electrons that I used. That's going to leave me 18 electrons, I hope. Those again are going to go on the outside in pairs of electrons. So 2, 4, 6, 8, 10, 12, 14, 16, and 18 electrons. I am out of electrons at this point. Is everybody good in this case? No, which one's not good? It is the nitrogen. It is actually short, right? So if we look around at our oxygen here, that is 2, 4, 6, and 8. All the oxygens are basically the same, so they all have 8 around them. But when we get to nitrogen, we got 2, 4, and 6 only. So it is short. It has not met the octet rule in this case. We have already obviously distributed all of our electrons. So we need to try to fix this. So can I fix it by just putting some dots there? I cannot, because why? Yeah, I now have 26 electrons, right? And my cutoff limit is 24 for this. So we can't just put electrons on to fix it. This is the case where we want to try to fix it with a double bond first. Now, does it matter which oxygen I double bond at in this particular case? It doesn't, because they're all the same. They're all basically identical oxygens. Whichever one you like, you could double bond. Can I just throw a line down? I cannot, for the exact same reason. I now have 26 electrons. And by the way, the oxygen on top would then have 2, 4, 6, 8, and 10 electrons. Doesn't have the same ring as the octet ruler there, right? So too many there. So when we're trying to fix a situation like this and we need to make a double bond, and by the way, when you need to make a triple bond as well, what you actually need to do is actually just grab a pair of electrons. And what you're going to do is essentially take those pair of electrons and you're going to bring them in to make that double bond. So you're just going to kind of bring those electron pair in to make that double bond. The result of that is I will now have a double bonded oxygen on top, because that's where I decided to do it. I will have still the single bonded oxygens on the right and left side. And now I could put a little bracket around it to make it all pretty looking, because it is an ion. So typically we do put brackets around it and the charge on the outside when we draw Lewis structures for anything that has a charge. But more importantly, what I have just done is I hopefully have fixed the problem. So let's make sure I did. That is 2, 4, 6, and 8 electrons for the oxygen on top. So it's good. That is 2, 4, 6, 8 electrons for that oxygen. So it's good. That is 2, 4, 6, 8 electrons for that oxygen is good. That is 2, 4, 6, 8 electrons for the nitrogen. It is good. I still only have, if I go around, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, and 24 electrons total. So I have still 24 electrons. I have fixed it by making a double bond in this case. And that would be the proper structure without all the highlighting on it. It would be the proper structure in that case. Question on that there. Now, could I have double bond to the right? The answer is absolutely. You could have double bonded to the oxygen to the right. And if you did double bond to the oxygen on the right, you would end up with a double bond on the right, and everybody else would still be single bonded. And of course, you could have double bonded on the left if you chose to do so. And you would have had a double bond on the left if you did that guy, which is again perfectly fine to do. All three of these structures are actually related to each other. These are what are known as resonance structures. Resonance structures basically happen when you have a situation just like this, where frankly you have more than one option as to where you could have done that double bond. The true reality is those double bond electrons are what are referred to as being delocalized, which means they're just moving around, which means at any given point, they could be over here at this oxygen, could be up there at that oxygen, could be over there at that oxygen. They're moving around, so they really could be located at any oxygen at any given point. One Lewis structure by itself may not perfectly describe what's going on, so you can actually draw three equivalent structures, and they're related to each other as known as resonance structures, usually with these kind of arrow headed in both directions between the structures is usually what you see. Do you have to draw all the resonance structures? The answer is no, unless the instructions ask you to do so. But if the instructions don't ask you to do so and ask you just to draw the Lewis structure, you could draw any one of the three, and that's perfectly fine. So any one of the three would do. But again, if you happen to come across an instruction that said draw all the possible resonance structures, then technically speaking, you're supposed to draw all three of those. Any questions on that there? All right, let's try a few more here just to make sure. Why don't you draw H2S? Why don't you draw SO2? Why don't you do a little CO2? Why don't you do a little CO3 2 minus and N2? So draw up some structures for each of those and see what you come up with. Actually, we'll do one more here. Let's do NH4 plus. All right, so take some time, draw them up. You need to take a break, you could break as well, and then come back and work on it, whichever way you want to do it. Okay, so let's take a look at some of these here, see how you're doing. Again, we'll start with the top left here. I'm going to calculate my valence electrons. So hydrogen is one, and there's two of them. So that's for our hydrogen. Sulfur is group 6, which means it has 6. So that is 8 valence electrons. We clearly know, right, hydrogen should never be in the middle. So we're going to go with sulfur there in the middle. Hydrogen could go on the sides. Once again, we're going to do our single bond. That's going to use 2 4 electrons. I now have 4 more to go, right, after I did that. So I got 4 more. Do I put dots on hydrogen? I do not, right? So remember, never, ever, 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 ever do that. Hydrogen is actually full, right? It's got 2 electrons on each side. That is essentially what hydrogen should always look like, just like that. No dots, nothing like that, one line basically. So what's left is then we're going to go to the center and go 2 and 4. At this point, we now have put all 8 electrons on it, and everybody is good. Hydrogen has, again, only 2. This hydrogen has only 2, and the sulfur 2, 4, 6, and 8. Everybody has 8 valence electrons around it, and a total of 8 total electrons as well. So once again, no hydrogens that look like this, yes, or triple bonded, none of those things. Yeah, so just a single bond hydrogen. All right, next one, we'll go right next door, which is SO2. Now again, 6 for the sulfur from the periodic table. There's 2 oxygens, each is group 6 for our oxygen. That's going to give us 18 valence electrons. Once again, if we look at the periodic table, sulfur and oxygen are in the same group. Oxygen is further up, which means it's more electronegative. That would tell us that sulfur should go in the middle. Again, just logic as well. One sulfur, 2 oxygens. Probably that's the guy in the middle. So we're going to do sulfur in the middle. We're going to do an oxygen and an oxygen. We're going to do a single bond, single bond. That is 4 electrons we just used there. That's going to get us about 14 more to go. Once again, we're going to work outside in to do that. So 2, 4, 6, 8, 10, and 12. At this point, I have 16 electrons that I put on this thing. I still have 2 more to go, right? So I still got 2 more electrons to put on there to get to 18. They go as dots on the central atom, and that is how they get there, by the way. They do not double bond on both sides or anything like that. They actually get there with the dots. Now we want to make sure that everybody is good. Is everybody good in this case? Which one's not good? It is the sulfur. Sulfur has only 6. So this is a situation where we could try to fix it by making a double bond. It does not matter, again, which one that you choose. But again, if you count up, sulfur has got 2, 4, and 6 only. So it is short. It needs 8. So I'm going to double bond here on the left. And a reminder that when we do a double bond or even a triple bond, we're going to take those electrons in to do so, to make that double bond. That, in this case, will give me a double bond there on the left. Did that fix it? Sulfur better now? It is. It actually has 8. That is actually good. We're actually good here. Everybody has 8. 2, 4, 6, 8. 2, 4, 6, 8. 2, 4, 6, 8. Everybody has 8 electrons around it. This is also one that you could have done a resin structure for. You could have absolutely have double bonded the other side. And you would end up with a structure like that. So again, either one would have been perfectly fine, as they are resin structures of each other. Any questions on that one there? Can't tell you how many people will have double bonded both sides of this with no dots or anything like that. So again, make sure you follow sort of the order there, and it should get you to a good picture. All right, CO2. We got 4 for the carbon, 2 times 6 for the oxygen, right? That's going to give us 16 valence electrons. Once again, if we look at carbon and oxygen, they're in the same period on the periodic table. Oxygen further to the right, which means, again, it's more electronegative. That tells us carbon is less electronegative. And again, that sort of logic of there's just one carbon, so let's put it in the middle, seems good. And we're going to do some oxygens on each side. We're going to do a single bond. That, again, is 4 electrons, 2 for each line. That means I got 12 more to go. Again, outside in. So 2, 4, 6, 8, 10, 12. At this point, I put on there 16 electrons. Yeah. Is everybody good in this case? No, carbon is well short, right? Carbon has only 4 electrons in this case, right? So again, we're going to make a double bond. It doesn't matter which one you choose. We're going to take a pair of electrons and move it in to do so. That's going to get us here a double bonded oxygen on the left. Did that actually fix the problem? No, it got better, right? Carbon is now up to 6 electrons, right? There in the middle. This case, can I double bond anywhere else? Yeah, I could double bond on the other oxygen. And that is what you would want to do before you leapfrog to a triple bond. Again, you want to kind of exhaust all your double bond possibilities, if there happens to be more than one, before you go to a triple bond. So we're going to do the same thing. We're going to take a pair of electrons and bring that guy in as well. And that's going to get us now a double bond on each side. And did that fix it? It did. Our carbon in the middle now has 8 electrons. And each of the oxygens on the outside has 8 electrons. So 2, 4, 6, 8. Carbon, 2, 4, 6, 8. 2, 4, 6, 8. Everybody has 8 electrons. And we still have a grand total of 16 electrons, right? Which is what we has to have. Any questions on that, though? Next one there. Rolling through. We got CO3 2 minus. So once again, 4 for the carbon. We have 3 oxygens, each are 6. Minus 2, what am I doing? I am going to add 2. Again, minus means I gained electrons, and 2 is how many I gain. So we do have to add that minus 2 charge into our total. 24 valence electrons here. So we're going to go carbon in the middle, as it's the least electronegative. We will do our single bond to everybody. That is 2, 4, 6 electrons. We got 18 more to go. We'll go 2, 4, 6, 8, 10, 12, 14, 16, and 18. At this point, I have now put on there 24 valence electrons. Is everybody good in this case? No, the carbon in the middle is short, right? Again, the carbon in the middle has only 6. Once again, we're going to double bond at any of those oxygens, and that would get us a double bonded oxygen there, single bonded there, and a single bonded there. Once again, since it does have a charge, we'll put some brackets around it and a -2. This is again another one that you could have done a resonance structure by just double bonding at any of the oxygens that you chose. So again, if you chose to double bond to the left, your picture would look something like this. And if you chose to double bond there to the right, your picture will look something like this. Once again, any one of those 3 pictures is perfectly good. And again, if you were asked to draw all of the possible structures, all 3 of the pictures is what you would want to draw in that particular case. Any questions on that one there? All right, so we got, we'll do NH4 plus next. I was going to flip the page, so we got a little bit more to write on maybe. There we go. So we'll go NH4 plus. Again, we got 5 for the nitrogen. There are 4 hydrogens, each is 1. And again, on the plus here, I should subtract 1, right? Because positive means we have lost electrons. So we do need to subtract the electrons out. That's going to give me 9 minus 1, which is 8 valence electrons. In this case, there really is no option other than nitrogen should be in the middle because, again, hydrogen cannot be in the middle for any reason. So we're going to do our nitrogen there, hydrogen's around. We're again going to do 1 single bond to everybody. How many electrons did I just use? That's 8. So I'm out of electrons at that point. Is everybody good? Everybody is good, right? Nitrogen in the middle has 8. Each of the hydrogen has our magic number of only 2, right? Also a little bracket around that to make it look all chemistry like there with a positive charge on the outside. Any questions on that one there? Last one was the nitrogen. And in this case, we have 2 times 5, which is our nitrogen, and that's 10 valence electrons. In this case, there really is kind of no central atom, so you just put them side by side, it's good to go. You could still do the exact same method we've been doing, even if there's just 2. You're going to connect them. That's 2 electrons, which means I have 8 more to go. Going to just put them on one of them. So 2, 4, 6, and 8 at that point. I am now out of electrons. Is both nitrogens good? Now, the one on the left has only 4 electrons, right? It's got 2 and 4, so it's quite short. The one on the right's good. It's got 8. So here we're going to try to fix it by making a double bond. We're going to take a pair of electrons and bring it in. That will get us something that looks like this. Did that fix the nitrogen on the left? It did not. It got better. It's now up to 6 electrons, right? It's got 2, 4, and 6. At this point, there is no other option for a double bond. So now we're ready to go to a triple bond in this case. And we could then take a pair of electrons and bring it in to make a triple bond. And that is how our friend nitrogen gets 3 bonds there, triple bond between them. And now we have, again, a total of 10 electrons. And everybody has 8, both of the nitrogen through sharing through that triple bond will reach the octet rule. Any questions?